So we were talking about the strategies to enhance the mesh quality. One of the first strategies we talked about is to decrease the face size. Okay, so we can do mesh, right click, insert, sizing. Okay, and as we said, for example, if we want to impose a certain size for the wall, we can put that, since we already named our part, we can select the name selection technique and select for walls. After doing this, we can specify the element size. So here, for example, let's say it's 5 centimeters, so it's 0.05, okay, meters. And that's it. In this way, we can impose the size of elements on the walls. Now, for example, we can do several sizings. So we can do sizing for the occupant also, for the inlet and outlet. In general, the occupant is the most critical surface because you have curves. So whenever you have curves, try to use a smaller size. So let's say for the occupant, we want to use a size of 2 centimeters, for example. So again, we do a new sizing, insert, sizing again. Now I want to select the occupant. So for the name selection, I put occupant, and I specify the size as 2 centimeters, so 0.02. Okay, and now then I created a face size for the walls, a face size for the occupant. Now, in general, okay, we try to avoid large differences in sizing on the same face. What I mean by this, for example, for the inlet and outlet, if you consider that they are important parts because you have flow through them, and maybe I want to use a smaller face size, do not use a much smaller size than the walls, because if you suddenly decrease the face size in a very fast way on the same surface, and because the inlet is on the wall, this will create a source of divergence. So if you want to select a smaller size for the inlet and outlet, it should not be much smaller than 5 centimeters. So you can try, for example, 4, or in general, we'll see this also as a definition of inflation. From a cell to cell, it's not recommended to change in size in a very fast way. So we recommend in general a ratio of 1.1 or 1.2, not more. Okay, so here, if you want to use, for example, 4 instead of 5, it's fine, but do not go very low in values. So let's say for the inlet and outlet, we want to use another size. So we can again do insert, sizing. Now look, in the name selection for the face sizing, you cannot select several parts at the same time. So if you put name selection and you selected, let's say, the inlet, you cannot also select the outlet. So you need to do them separately. This is why here it will be better to use, instead of doing 2 times the sizing, you can do geometry selection in this case, and then select 2 faces. Okay, so you can select the inlet and the outlet. So I can select here first inlet, let's say, then I turn and select also already the outlet was already selected because in the name selection part. So now you have both selected, inlet and outlet, and you put apply. In this way, you were able to impose the size on these 2 faces by using the geometry selection mode. And now you specify the element size, let's say 0.04. Okay. Now we still have, now for the ceiling and floor, you can use the same size as walls. So if you want here also, we can do another face sizing with geometry selection to select both floor and ceiling. And you could have, if you want, from the beginning with walls, You can select ceiling and floor by using the geometry selection. But since already we have done the sizing for the walls, so now we'll just do the geometry selection for the ceiling and floor. So we select these two. So let us zoom a little bit in, zoom out, and then I can turn to select. Don't forget, when you want to select several faces, press on Control. Okay. So now my two faces are selected. I put apply, and I can determine the size, like walls, as we said, 0.05. Okay. So now I have a different sizing for my different parts. I am done. I did sizing for all parts. So I expect that the quality of my mesh will be enhanced. So again, I do mesh, generate. Before generating mesh, if you want to select a certain type of elements, you can just do mesh, insert method. Okay. You can keep the automatic method. So by default, ANSYS will select a method, or you can impose the method you want. First, when you select method, you select the geometry where you want to do the mesh, which is your room, and it's a volume selection. So as you can see, the tool automatically is the tool automatically selected is the volume selection. Okay, so you just press on your room, it will be selected, and you put apply. And now you can specify the method. Automatic means that ANSYS will do what seems convenient for him, ANSYS Fluent, or you can, for example, say, I want to impose using tetrahedrons elements, or I want to use another method. So you are free to select what you want. And now we can do update. So you generate mesh again, and you can test the quality. You can observe the quality again. So as we have talked about, you have the skewness, you have the orthogonal quality. Another important factor is the aspect ratio. Okay, the aspect ratio, if you want, will test the stretching of an element. It will measure the maximum dimension over the minimum one. It will take several dimensions into consideration, heights, lengths of edge, etc. So it will divide the maximum over the minimum. In general, we recommend aspect ratios near the walls, a maximum ratio of 10/1, and far from the walls 5/1. Now we can accept larger ratios, but it's recommended to remain in this range. Okay, so let's say a maximum below 10 will be fine. Okay. So, because in general, we have the largest aspect ratios near walls, because we'll see after that we'll do sizing at walls, and as we go far, we can go with larger elements. So this is why we expect that near walls aspect ratio will be larger than other places. So this is another criterion you can look at when you look at your mesh quality. So now we'll wait some time. It will take more time than the previous mesh, because now we did what we call refining. We refined our mesh. We are using smaller size for our elements. So we expect that the number of elements, of course, will increase, and the mesh quality hopefully will be better. Already our mesh was good because the space is not very complex, but believe me, if you have a complex space, it might take days to achieve a good mesh quality. So it's done. Now we can go to verify the new quality of our mesh. We go again to mesh. And as you can see, if you compare the previous mesh to this one, you can see how much the elements are much smaller here, and then you have much more elements. You can check for the number of elements in the mesh. So you have here in the characteristics of mesh, you can determine what is the number of elements, what are the number of nodes, etc. Okay, so here, for example, you have several characteristics that are given, and you can explore them, and you can look also at the number of elements and nodes here in the statistics. So you have, for example, here you have 694,992 elements. So this is acceptable if you want. You are below 1 million, it's fine. Okay, and you have the number of nodes. Now, to know what is the number of elements required, so first you test the quality of the mesh, and also when you perform your run, you can do what is called grid independence test. So you try to vary the number of elements to decrease it and compare the result. If you are not having a large change in result, so if the change in result is below, let's say 5%, then you can say, okay, it's better for me to use a lower number of elements because it will take less computational time. So of course, it's good to have a low number of elements, but we should have accurate results. So we should compromise between accuracy and computational time. When we do the runs, when we do calculations, we can perform several runs on different mesh, and we can select, if you want, the mesh that will give us accurate result with lower number of elements. This is what is called grid independence test. So we do this in order to select a mesh that will not take a lot of time in computation and will give at the same time accurate results. Okay, so here we can check now, as we did before, for the characteristics. As you can see here for the mesh metric, concerning the skewness, we are still below 0.95, which is fine. We can compare with the previous one if we know already the values before. You can just put a table and see how the skewness is varying and how the average is varying. So you can determine if your quality is enhanced or not. You have the orthogonal quality also, you can check for it. The aspect ratio is here, for example, also. You can investigate the minimum and maximum value of it. And as we said, it's good to have values lower than 10. Okay, so here you can see the minimum, the maximum, and the average. So for example, here's the minimum, the maximum is below 10, which is fine. In general, as we said, near the walls, it should be below 10. And already the maximum in the space is below 10, so it's fine. Because in general, walls are the critical places where you have change in, where you have stretching of elements. So this is for the aspect ratio. We can check also for the orthogonal quality. For example, you can keep the method automatic, because when you keep it automatic, ANSYS will have more comfort in choosing the appropriate method. If you don't want to impose a certain type of elements, so he will do the automatic way and select the corresponding type. So sometimes this might work better. Okay, so you can try several strategies. Here, for example, if we compare with before, nearly the average is still, it was 0.77, so it's still nearly the same, but the minimum was larger. So what we did was not very efficient. So we can, for example, try to keep the method automatic, or if you want, we can try a different size for inlet and outlet. Okay, so you can try to change the properties in order to get good quality. And if, for example, maybe putting the inlet and the outlet different than the wall created some problems as size, so we can keep it, for example, we can keep it equal to 5 centimeters. And since we are having a lot of elements, maybe for the occupant, we can put a size larger than 2 centimeters. So we can say that for the occupant, we can work with 3, for example. So we can try different combinations, because as I told you, it's not advised to have very large differences between face sizing of surfaces. So even that the cylinder, it's true that the cylinder is far from the walls, but it's close to the floor level. So if you put the occupant 2 and the floor is 5, you have a sudden change in the sizes. This is not good. So this is why maybe the mesh quality was not enhanced. So you should try then to maybe or decrease the size of all walls and floor ceiling, or increase the size of occupant to not have a sudden variation between the two. Okay, so let us try, if you want 4 for the occupant, if we choose 5 for all others. And we can use the automatic method, for example, for Fluent. So Fluent will select the appropriate way. Okay, and we can try again to see if this is better. So in general, it's trial and error in the meshing enhancement quality. You have some known strategies, and decreasing the face size is good. We should avoid sudden change in sizes for surfaces that are close to each other. So you can play with these techniques and until having a mesh that is satisfying you. In our problems, the mesh was good from the beginning, so we could have just done the automatic method of Fluent without introducing any sizing, because the quality of the mesh was fine. But I am introducing this because in most complex, in more complex geometries, you need to enhance the quality of the mesh to get accurate results. So we should know what are the strategies that can be used to enhance the mesh. So here it's meshing again. It will take some time as usual. So after face sizing, I will introduce for you a new technique, which is inflation. What is inflation? In general, for a surface, okay, for the walls in particular, you might have formation of boundary layers. You know from fluid mechanics that flow over a surface will cause the development of a boundary layer. And in this boundary layer, you have several zones. You have the first layer, that is the viscous layer, sublayer. You have a transition zone where you have a transition from laminar to turbulent, and you have the core region. So in general, the wall is critical. If you want to trap the physics within the wall, it's important to have fine size near the wall. One strategy is to use face sizing, but sometimes, as I told you, because in ANSYS, you should go smoothly from one side to the other. If you reduce a lot the face size, then the transition within the space should be done smoothly. And this will cause a very large number of elements. The inflation will just, if you want, will consider a certain zone close to the wall and will divide it into small layers. Okay, so you can have, this zone will be more accurately trapped. If you want, you can trap boundary layers in this zone more effectively without having to increase a lot the number of elements. So we'll talk more about this strategy now, but before doing that, let us check the mesh is done. Let us check the new quality. You can always check how the number of elements is varying and how the number of nodes is varying. Now, concerning the orthogonal quality, still nearly the same. So you can say that this is fine because all criteria are satisfied. The minimum is larger than 0.1. The average is close to 1. It's acceptable. For the aspect ratio, So for the aspect ratio, we can check that still the maximum is below 10. So nearly our methods are fine. Yani all strategies we done are giving nearly close results. So we can work with this mesh. Okay. Now, in case your mesh was not convenient, you should try to change your strategies by using phase sizing, using inflation, changing the method of dividing your space and the type of elements, etc. So you should try different combinations until reaching the desired mesh. And concerning skewness, okay, so also here we have the maximum is fine, it's lower than 0.95, and the average is low, it is good. Okay, so this is for the phase sizing technique. Now we were talking about inflation. I will detail it more now in a sketch, but how to introduce it? We press on mesh, right click, insert, inflation, and we can press on. Now we want to apply inflation on what? In general, okay, inflation is applied on surfaces, okay, and these surfaces are in contact with the room. So first, for the geometry selection, we'll select the space, okay, and we'll put apply. And now, what is nice for name selection, for inflation, that you can use name selection for multiple faces, not like face sizing. So here, if you want to do inflation for all of your surfaces, okay, you can just put name selection and here select all of these surfaces. So press Control, you press Control and you select all of them. I will tell you why I will do a selection for all of them, not for just a certain surface. Okay, and now you can determine the number of layers needed. So you will do layers near the surface. I will illustrate it for you in a sketch to understand how. In general, as I told you, the growth rate between the size of layer and another should not be very large because this will cause high variation in size of divided elements. So the growth rate is advised to be below 1.2. We can put it as 1.1. And now we'll press generate. And during generation of mesh, I will explain for you in detail in a sketch what is inflation. Okay, so let us open a new window. Okay, so you have a surface and you have elements. So let's say you are using, for example, as we said, I will take a simple example first, a rectangular grid. Okay, let's say it's a rectangular grid like this. You have your elements. Now, since the wall is a critical surface, okay, you might need just to, if you want, create very fine elements near the surface without increasing a lot the number of elements in the whole domain. So since this zone is of interest for me, inflation will do the following. It will create layers near the surface. So for example, like this, if you put 5 layers, let's say It's 1, 2, 3. So it will put layers, and these layers will begin by a layer that is very thin, and the thickness will increase by giving the growth rate. So if you use a growth rate of 1.1, this thickness will be multiplied by 1.1 for the second, by 1.1 for the third, okay, etc. So you will divide your element into 5 layers, okay, and in this way you will be able to trap what is happening in this zone in a more effective way. Okay, now why I told you we should do it on all surfaces, not just on one, because for example, look, if you have walls, this is a wall, and you have a second wall from this side here. So let us choose the black color again. So this is another wall. If you do just inflation for this wall and you leave this one, what will happen? You will have a sudden cut in the inflation, which will lead to divergent zones. While if you do inflation for all of your surfaces, the inflation will be continuous. What I mean by this, that here, for example, the inflation will be like this. So you'll not have a cut in your inflation. It will be like this. Okay, and in this way, you will be able to divide your zones into smaller, and your interesting zones into smaller parts without causing any discontinuity in these regions. Okay, now when we see the mesh together, I will do a cut for you so that you can see how inflation is done. Okay, so for example, for the cylinder, this is the cylinder, inflation will be done like this. So because you already done inflation on the floor, it will continue from the floor towards the cylinder. It will not be interrupted at the occupant. It will be like this. It will surround it, which is much better. If I just do inflation on the floor and I don't put an inflation for the cylinder, I will have a problem here where the layer will stop. Okay, so to avoid this, we try to have continuity of inflation. Okay, now we'll see this in ANSYS, how it will be done. So let us check inflation. How can I see inflation? To see it, I cannot see it just by looking at the outer of the room. I should do a cut. I should cut my room and look inside of my room. How to do this? I have a cutting tool. So first, let me zoom a little bit. Okay, look, this is the cutting tool. I can create a cut in the location where I want. Okay, then I can look inside what is happening. So let me put mesh. Okay, so as you can see here, look, I'm not seeing very well, so I should do a small zoom. If I do a zoom in, you can see how near your cylinder, okay, I created 5 layers. So as you can see here, you have 5 layers. 1, 2, 3, 4, and 5. Okay, and you can see the smooth transition between sizes near your cylinder. Now, also for walls, you can check that for walls also inflation is working. You can see here, you see how you have continuity of your inflation. You do not have a cut because you did inflation on all of your walls. So imagine that just you did for one of your walls, so you have a problem. It will be interrupted suddenly, your inflation, which will create problems in computation, and it might lead to divergence. So we should pay attention for these strategies. Now, inflation in general is used to trap boundary layers. Okay, sometimes it can affect in a bad way the quality because it will create here like a small change, a fast change in dimensions. But we can always try. So if inflation will not affect in a very bad way our mesh, it will be good to put it because it can trap better boundary layer formation. In case it's not working and it's affecting in a very bad way the quality, we can replace inflation by reduction of face size. So reduction of face size, but this will increase a lot the number of elements. So always you should do a compromise between computational time and accuracy. So you should try to have a very good accuracy with a low computation time. So you should try several meshes and then decide which one is the most appropriate. Okay, now let us check what happened with our mesh quality. So we just press on mesh. We can see here the number of elements has increased compared to the mesh just before. We have for the statistics, concerning the skewness is still fine. Okay, concerning the aspect ratio, look here, for example, okay, as expected, sometimes introduction of inflation will decrease the quality because look, the maximum of the aspect ratio has increased compared to the previous mesh. In general, 11 is larger than 10, but it might work. Yani, if you go to your we say it's advised to be lower than 10, but to have good results, you still have values. If the value is close to 10, it's fine. And sometimes you can go much higher and the work will still be fine. So to verify, you can always do a preliminary run, see if your results are physical, okay? And you can do validation with experiments to see if your CFD model is giving accurate results or not. To be on the safe side, you can say, no, I don't want this. So I want to keep it below 10 to be on the safe side. So I can, let's say, maybe change the growth rate or change the number of layers, anyway, to keep it below 10. So I can try to do several other strategies, but still 11 is fine. It's not very far from 10. And even if you read, they tell you that you can go up to 35 aspect ratio and still have convergence in the thermal and velocity field. So a value of 11 is not bad, okay, as maximum. And finally, for the orthogonal quality, so what I want to tell you, these numbers I gave you, it's good to be below them, but it's not, if you are above them, it doesn't mean that your mesh is bad. So you might still have convergence. So what you can do, you can do runs and compare different meshes and see if I have an aspect ratio a little bit larger, if this will affect a lot of my result or not. And finally, for the orthogonal quality, so as usual, we said it's good to have an average orthogonal quality close to 1 and a minimum higher than 0.1. Okay, so there is a small problem with this. It's fine. So we can check for the value of orthogonal quality. In this way, we have seen the different strategies to check for the mesh quality, how we can improve it, how we can obtain a good quality of a mesh, what are the strategies that can be implemented as phase sizing, inflation, selection of type of elements, etc. So here we can see that for the orthogonal quality, it's still acceptable. I told you that inflation might decrease the quality, but the importance is that the quality is still acceptable because the minimum is still larger than 0.1 and the average is close to 1. Now, inflation might be is of high importance when you have if you want to study boundary layers, and if you have heat sources and you are relying on buoyancy effects, you know that by convection and buoyancy effects, you have formation of plumes, you have formation of thermal boundaries and flow boundaries. So if these are very critical in your problem, it's good to use inflation. If not, you can remove inflation, okay? And you can try different phase sizing in order to get the best quality while not having a very large number of elements. Okay, so since this mesh is working fine, even with inflation, so because the inflation did not drastically change the quality is still fine. I can keep it because it's good for me whenever I have to study a flow field where I have formation of boundary layers. Inflation can enhance my results, so it's good to keep it. Okay. Especially here, for example, if you want to study, for example, displacement ventilation room, where you introduce the flow from the lower level. So here you should change then your inlet location. So here we considered a mixed ventilation room. We place inlet and outlet at the top. In case you want to study a displacement ventilation room, you should have the inlet at the bottom and the outlet at the top. So in displacement ventilation, you rely a lot on buoyancy effects. So formation of thermal plumes is of high importance. So it's good to have inflation to trap these boundary layers. Okay, so this is for different strategies of meshing. Now, once you are done, okay, at each step you can save your file. To save, you can save everything. Just you go back to the main file. So you go back to your workbench. Okay, now look, since here you still have this symbol, okay, to have a green tick, you just should click, right click, generate. So it will update the mesh from here. So here you can put update. You should observe a green tick close to the mesh and this will tell you that it's fine, the mesh is done, it's working well. So here, by just clicking on update, you will have the green tick instead of the yellow symbol. And once you have it, you can save your project. Okay, you just have to click file, save as. You can name it as you like. Put it, you can in general save it in C or D, it's better because it will take some space. Okay, and then you can exit and go back to your file whenever you want. So here, as you can see, the geometry is ticked in green, the mesh is ticked in green. Now we are ready to move to the setup. So in the next step, we will see how to define the boundary conditions in the setup. So now I will just put file, save as. So here, for example, we are studying ventilation in the space. You can name your file, for example, ventilation. You can use any name, okay? So ventilation. And just we click save. And now we're ready to proceed to the setup phase.